Interview prep really has two halves. The first half is problem solving. That's the foundational half. And then once you have solved a problem, then you need to express it in some programming language. So that's where coding fluency comes in. So let's talk about both of these uh, in a little more detail. What is problem solving? Well, a problem is defined to be a question for which you have no idea initially what method will work to solve it. Which means, as soon as you're given a problem, by definition, you start out feeling clueless. This is in contrast to an exercise. An exercise is a very different type of question. For example, if I give you these two large numbers to multiply, it's not a problem for you because we've all done grade school arithmetic. We know how to do long multiplication. It might take us a lot of time. We might make calculation errors, but there is no mystery about what method is needed to solve this question. A problem, in contrast, has that element of mystery. And because it's mysterious and enticing, we need to spend time investigating it properly. And what I mean by investigation specifically in our context is trying out different problem solving strategies to attack it. These problem solving strategies depend on the domain from which the problem comes. So, math problems have their own strategies, scientific problems have their own strategies. In computer science, uh, the problems we see have their own strategies. And the problem solving strategies in computer science are basically the algorithm design strategies, right? In particular, I cover four of them in the pre-class videos: brute force, decrease and conquer, divide and conquer, and transform and conquer. Those are the broad problem solving strategies that can be used to attack any algorithms problem. And we'll see how to do that throughout today's class. So, why are problem solving strategies equivalent to algorithm design strategies? Because the solution to a computational problem is really an algorithm. An algorithm is a method that solves the given computational problem. And the intent of an ideal technical interview is to see how well you can design an algorithm. So when they're testing problem solving, they're really testing how well you can design an algorithm. That algorithm needs to be correct. That's the first requirement. It also needs to be efficient. So generally we express efficiency in terms of the time and space complexity, and we look at the worst case for the most part, with some exceptions, but generally the worst case. So once you have designed a correct and efficient algorithm to solve the problem, and you agree on that solution with the interviewer, the second part of the interview would expect you to implement that algorithm as a program. So together, problem solving and then coding, together these test three things. Your problem solving skills are tested, your coding skills are tested, and both of these depend on an underlying foundation of um, fundamental knowledge of computer science and engineering principles. So what we do at IK is we provide you these fundamentals via foundation videos or pre-class videos. So the purpose of the pre-class videos is to provide you those fundamentals and also do a little bit of problem solving. But the problems we solve in the pre-class videos are standard problems for which the algorithms are standard. So the live class is where we focus on problem solving skills, and to some extent I also walk you through coding patterns which are common to several coding problems so that you can use them, whatever language you're using in your interview, you could apply those patterns and code up the solutions. So this is the intent of an ideal technical interview. What happens in a real technical interview, though, is that you don't have much time. As I said, problem solving requires um, sustained investigation, and so that means it requires time. And a real interview is a time test. Whenever you're given a time test, there's going to be anxiety. This is true for kids. Many kids have math anxiety because of these timed math tests. And it's also true for experienced engineers. Many experienced engineers go through uh, massive anxiety when preparing for interviews, or even in an interview. Many people tend to have a brain freeze. Why is that? Because you're being evaluated on the spot in a timed environment, and there is a tension between giving you a time test and testing your problem solving skills, because problem solving needs time. So how do we resolve this tension between um, problem solving and the severe time limit that a real interview has? Well, there are two approaches we could use to tackle this tension. The first approach is to prepare in a way that every interview problem is an exercise, right? So we mug up the solutions to the 1500 or so lead code questions that there are today, hoping that every question you will see in the interview will be a question that you have seen before. So there's no mystery as far as what the algorithm is. The focus is purely then on how to code it up. And that's the path that many people follow. And it has to be admitted that for some people it does work. I know a few friends uh, who have got um, every single question they were given in Facebook was a question they had done before. A couple of years back, there were like 30 questions on lead code for Airbnb, and a friend of mine, he just prepared for those 30 questions, and every single question he got at Airbnb was from that set. So he got an offer. So that's easy, right? That's the best case. The problem with this approach is that if you are given a question you have not seen before, you are going to have a brain freeze, right? You're depending on luck. Sorry, I need to reshare here. You're depending on luck, and a friend of mine who I'm talking about, he failed his Google interview because Google, as a policy, does not tend to give questions from lead code. In fact, he didn't even remember what questions he got after the interview because he just hadn't prepared well. So, um, but 2 years back, it was still possible to memorize 400 or 500 solutions. Now there are more than 1,500 questions. How much are you going to memorize? Right? And you're still dependent on luck at the end of the day. So that's the first problem. The second problem is that this approach does not help you become a better engineer. Interview prep is a time when you can relearn your computer science skills and understand how real world systems are designed in systems design. And if we prepare properly, then no matter what job we take up next, our performance in that job will also be much better, right? Since we would have become a better engineer. So because of these two issues with the first approach, we follow the second approach here. We want to teach you how to become a problem solver so that you develop an inner confidence. This inner confidence is the antidote for anxiety in an interview. Once you learn repeatedly to solve questions you have not seen before in your preparation, you develop this inner confidence, and when you walk into the interview, you know that you have solved many such questions before, right, throughout your prep. So it's not a new situation for you. At the same time, we would expose you to the popular interview questions so that in the best case, maybe the questions you're given are identical or at least close to questions that you would have done in your prep. And moreover, we would provide you those questions grouped by coding patterns. So rather than solving one random problem after another, we will walk through clusters of problems at the same time, which all have the same coding pattern. So that way, as you're solving each problem in that cluster, the same coding pattern is getting reinforced. So somebody asked on Discord, how can we prevent ourselves from forgetting the implementation that we did a month ago? Well, this is how you can alleviate that. If you instead of solving one random question after another, if you can um, group together questions which have the same coding patterns, so when you solve those 5 or 6 problems, the same pattern is unconsciously getting uh, repeated and reinforced in your mind. So even if you forget like you can't memorize code, but you would memorize the pattern. Not consciously, it would happen unconsciously. It's not like we are trying to memorize and hack the interview. It's just that it would be a side effect, right? Just like initially when you're learning to drive a car, you have to pay a lot more attention to every single move that you're making. But once you get comfortable, uh, your brain trains itself to think in certain ways, and then you after a certain point you stop thinking about the little things that your hands and feet are doing. So at IK, the first time you're given a problem, you should approach it like a problem solver, which means spend as much time investigating as possible, right? Because if we don't prepare ourselves in this way, then we are not preparing for the worst case. We are likely to have a brain freeze in the interview. So even if we give you popular interview questions as problems, avoid looking up their solutions. Because if you don't exercise those brain muscles to train yourself to become a problem solver, you will not be able to use those muscles in the interview. Many popular interview questions will eventually become exercises by the time you finish your prep here. But you should not forget the first time, the original journey that you followed to solve that problem, because you might have to quickly retrace that journey in the interview to show the interviewer that you're not just retrieving the solution from your memory, like retrieving an entry from a hash table. You actually know how to uh, think about the given problem from scratch, approach it like a problem solver, and find your own path to the solution. Now you will do multiple passes through each question. You should do multiple passes through each question. The second time you come back to the same question, it would no longer be a problem because you would have solved it before. You would be able to recall what method worked, what algorithm worked. So that is the time when you try to improve your coding fluency on it, because problem solving can't be sped up, but the coding fluency part can be sped up. So you want to ideally not have to worry about both in an interview. You want to spend your energy on solving the problem. Once you have solved the problem, you want to use one of the coding patterns that you have learned here, so that you're not writing this code from scratch. You know what the structure of the code looks like. It's just a matter of filling in the details. Now, there is a shift in mindset that is needed if we want to become a problem solver. There is a certain change in our mental discipline needed. Many of us may not be used to thinking hard about a given question for more than 5 or 10 minutes. We might feel tempted to look up the solution. Well, since problem solving involves embarking on long wild goose chases and doing open-ended experimentation, clearly the time scale of concentration required needs to increase. So um, as a rule of thumb, you should spend at least 1 hour to an hour and a half struggling with a single problem uh, before I would not even say looking up the solution, before seeking the minimum possible hint that is needed to unblock yourself, right? To take the next step. You could even take a break. Taking a break after thinking hard for an hour and a half is a good idea. You could sleep over the problem and then come back to it the next day or later in the day, and then spend another session, an hour, hour and a half, whatever. I mean, this is a subjective decision. Different people might have different, schedules for when they're going to be interviewing. But if you have time, I would even recommend spending an entire day on a single problem, because that's when you're really exercising those muscles and developing that concentration and patience needed. We also need to have this attitude that many different paths that we try to solve the problem are going to lead to a dead end. But that investigation is always worthwhile, even if it leads to a dead end. Why is that? Because there are lessons to be learned from those failures, which can prevent us from making those mistakes again for some later problem in the future. So we have to have this ability to extract generalized lessons from individual failures. So these are two changes in our mental discipline that we need. Increase the time scale of concentration and look at failure as a natural part of problem solving. Right? Without failure, there is, that it's meaningless to even talk about problem solving. You start out from a state of cluelessness. So when you have no idea what method will work, what is the option? You have to try out different problem solving strategies one by one, and many of them are going to lead to dead ends. So it's a natural part of the process. Secondly, we need to change our emotional attitude towards these type of questions. Many people have an aversion to be given for these types of questions, because they think that if you can't immediately see the method, somehow either you're not smart enough, or there's something wrong. Well, there's nothing like that. Many of us like solving puzzles, right? We enjoy puzzles because of the challenge that those puzzles offer. If the puzzles were too easy, it wouldn't be fun. So we don't mind spending hours working on puzzles. So treat these problems like puzzles. They are puzzles, in fact. Many of them are puzzles in computer science. And so we want to have the attitude that problem solving is more like hiking rather than working out at a gym. Solving lots of exercises is like working out at a gym. You're repeatedly doing the same motions over and over. It's not fun. You need headphones to listen to music or something to keep yourself entertained. But when you go for hiking, the journey itself is enjoyable. Independent of reaching the destination, you enjoy the path leading up to there. And you feel lost along the way. You get dirty, you get rained upon. It can often be frustrating. But if you don't feel lost, you're not really an explorer. Right? And at the end of the day, when you reach your destination, there is a lot more satisfaction from uh, from hiking rather than just finishing whatever sets of exercises that you had planned. So problem solving is an art, but it is also a craft, which means to some extent it can be taught and learned. Part of learning to become a better problem solver is to build up a foundation of background knowledge, which you would draw upon to solve problems. We provide you that in the foundation videos, as I said. We also want to learn from other people, because there is not much time to make all the mistakes yourself. In fact, you may not even think of all the different paths that you could follow to solve a given question. So if you share your solutions with other members in your cohort on your Discord channel, you can learn from each other's failures, try to help each other, and also learn from each other's both failures as well as successes, because for many of the questions, there may not be a single correct and efficient solution. There could be multiple, and there could be ways of solving the problem that you have not thought about earlier. Um, so again, going back to that hiking analogy, there might be different paths that lead up to the top of a mountain, and you followed one path and got there. But it's always nice to listen to the experience of other hikers who have reached there following, other paths, as well as those who couldn't reach there but ended up somewhere else. You could learn from, their experience because you didn't follow that path yourself. So um, like hiking, problem solving is an active process, which means you can't passively sit in a class and learn it, expecting the teacher to, download a whole lot of information in your brain. That's not how you learn to solve problems. You have to learn to hike yourself, right? Hiking is not something you can learn by sitting in a class. So this class, as I mentioned yesterday, is analogous to the talk or a short guided tour given by a ranger at the visitor center of a national park. You will learn about the primary landmarks in this terrain of sorting. So you'll have a broad understanding of what all is out there, and we will see how we will build tools. We'll try to, as I lead you through this tour, you'll see how to use these problem solving skills to approach questions you have not seen before. And then after the talk is over, the national park is wide open for you. And there are thousands of trails. So you could pick any of them and start hiking yourself, applying whatever you learned in the guided tour. So that's the attitude with which at least I teach the class. So this is my personal view of problem solving, and different instructors, might look at it in different ways here. For some reason, Zoom keeps freezing here. So right now we haven't yet begun that tour. We're still inside the visitor center. But before we step outside, I hope you have all sat down inside the visitor center and gone through those 6.5 hours of videos. Many times you go to a national park, there's a movie inside the visitor center that plays. So there are 8 primary sorting algorithms that I went through, not really as a laundry list, but more as natural outcomes of following different algorithm design strategies for the sorting problem. So before we step outside, let's just make sure we are all on the same page by reviewing what we should have what we learned from the foundation video. So suppose you're given this problem. This is on LeetCode. It looks simple enough. You're given an array of integers called nums, and you want to sort the array in ascending order. How would you do it? And there are 2 examples given here. If your input array looks like this, your output needs to be in ascending order. And even if there are duplicates in the input, your algorithm needs to handle duplicates. Okay. And you're also given some additional information, like how large the size of the array can be and what the values of those numbers could be. So if you're probably seeing this question for the first time, but does this look mysterious to you, or you think you know how to solve it? I'm assuming you know how to, it's not completely mysterious. So what algorithm would you use?
Quicksort or merge sort?
Counting sort.
Counting sort, okay.
Because range is very less.
Okay. Any other answers?
Divide and conquer, Quicksort.
Divide and conquer, okay. So which type of divide and conquer? There are 2 different.
Type?
There are 2 different ways of applying divide and conquer, and I'll elaborate on them again. But
So Omkar, this is Joy. We can try with, as the range is really small, right? And the O of n square, log of n will not matter much. So we'll try with the selection sort of the bubble sort.
Because it
okay,
is
could you increase your volume a bit? I could make out only a few words, Joy.
Is it fine now, Omkar?
Yeah, yeah, it's fine.
What I'm telling you, as the range is really small, right?
Hmm.
O of n square and n log n will not differ much, right? So I will go with the selection sort of the bubble sort.
so because it's having duplicates, we might also think of a stable sorting algorithm.
Okay, stable sorting. Right, but what you're doing is you're sorting integers here. So when you only have integers, do you think stability matters?
Not much, but we can ask that if
Maybe Heapsort.
Maybe Heapsort. Okay, so let's go through the options one by one. Somebody mentioned selection sort. So selection sort would what's the complexity of this? The worst case complexity. Typically, whenever we talk about complexity of algorithms, we are looking at worst case complexity.
It's
Order n square.
Big ones.
Right. So given that there are n log n worst case complexity sorting algorithms, we generally don't, prefer quadratic time algorithms, because as soon as you jump from n log n to n square, it is actually a very significant jump, because as soon as you move to n square, the maximum size of the problem that you can solve comes down to a few tens of thousands, whereas with n log n you could go up to millions. So for that reason, we would probably not use selection sort.
Don't you think we should look at the ranges in the test case, because you could spend 20 minutes designing the algorithm and then find out it's going to fail in your test case, only for you to abandon that approach, because you want to sort of be as optimal as possible, given, you know what I'm saying? Because like selection sort, insert sort, I doubt very much you would even really code that, because they perform so badly. That's not even worth the cycle sometimes to even go about doing that.
Yeah, so that's true. But when we look at it from a problem solving perspective, selection sort, even though won't lead to an efficient solution, it often provides a good starting point to then improve upon. And you'll see this at multiple points today, that we will start out with something that looks like a bit like selection sort, and then when we reach the dead end there, we will see another path leading out from there, which we will follow, and that might lead us to an improved solution. Yeah. The second option that I had in the videos was bubble sort, and the whole point of giving that anecdote from Obama was, even if you are completely clueless and you have a brain freeze in an interview, at least you should be able to say that I'm not going to use bubble sort. Okay, so don't mention bubble sort in an interview.
Why not merge sort?
Merge sort, yeah. So merge sort is certainly an option. I'm going through the algorithms in the order in which I think I mentioned them in the videos. Insertion sort, what's the worst case there?
So
N
it's
squared.
n squared.
N square. So based on this, we wouldn't use insertion sort. But having said that, there are some circumstances where insertion sort is useful. One of the features that insertion sort has is that you can write the code in a way that it's stable. It's possible to maintain stability. So, and it works quite fast on small arrays. So when your input size is really small, insertion sort might be good enough. And because it's stable, even if you had a small array of objects, you could use an algorithm like insertion sort.
One question, what do you mean by small? What is the size it is small?
So let's say about 30 or 40.
40,000?
No, just 30 or 40.
Oh, okay.
Small as in, that size. So I think I mentioned some hybrid algorithms in the pre-class videos, like Heapsort, for example, which is really a combination of merge sort and insertion sort. So when you start out with a very large array and you keep dividing and conquering it, you don't come down all the way to size 1, right? As soon as you are at sub arrays that are of size 30, 40, 50, something like that, you can directly use insertion sort instead of continuing the recursion down.
That's good.
So that's one scenario where you might use insertion sort. Another scenario is if your array is almost sorted. Right? Maybe it's quite big. The array size is quite big, but only a few elements are out of order. Let's say 5 elements are out of order. Right? So in that scenario, when you use insertion sort, it would end up doing work only on those 5 elements that are out of place. Right? Whenever it reaches a number that is out of place, it looks at assuming that the sub array up to that point is sorted, it tries to insert that number into its correct place. So it would do that work only for those 5 elements. And the amount of work needed for each element is in the worst case order n. So if there are 5 elements out of place, insertion sort would end up roughly working in linear time.
When would we know if array is almost sorted?
You need that data, of course. We typically wouldn't use it in a general interview problem where the test cases can be completely arbitrary. But in real life, if you know that only some elements are out of order, you would end up doing something like insertion sort. In fact, I think Heapsort starts out by trying to construct these small subarrays which are locally ordered, almost ordered, right? And it does that using insertion sort. And then once you start out with a large number of small sorted subarrays, then you can start merging them together. Okay, Alison, you raised your hand. You had a question.
Insertion, so almost sorted arrays time complexity will be is O n, yeah, linear time.
Yeah, on almost sorted arrays, it would be linear time, because when I say almost sorted, that means the number of elements that are out of order is a constant number. And if for each of them insertion sort spends order n time, the total time is order some constant times n, which is order n.
If you have multiple elements, multiple elements, we can use insertion sort is because stability is important. I think is insertion sort. If we have multiple elements, for example, multiple elements, can we use insertion sort?
Yeah. You mean, when you say multiple, you mean duplicates?
Yeah, duplicates.
Yeah. So the question of stability comes in only when there are duplicates, right? Because stability means that if you have multiple copies of the same number or same object in the input array, you want their relative order to be preserved in the output as well once the array is sorted. So, but having said that, stability is something we care about normally when you're trying to sort objects that are, that have other fields as well. Here, we only have integers given to us. So it doesn't matter which of the 2 ones here appears first, right? Because as far as we are concerned, they're identical. But if these integers were keys of more complex objects, then it could matter which of them appears first, because they could differ in those other fields. So Heapsort, for example, is a general sorting algorithm. It doesn't assume that the input is in an array of integers. It could be an array of any kind of object. And when you're implementing a general sorting algorithm like that, it's good to have stability. So that's why, yeah.
Sorry, I was just curious. Why do we care more about like worst case scenarios than average? Because you were saying like, oh, well, if it's a small array or it's almost sorted, doesn't that kind of approach like what the applicability of like the average?
Yeah. So the problem with working with averages is that you you need to know a priori what the distribution of your input is going to look like, right? Only then can you talk about averages, because the distribution could be skewed in one direction or another. So if you have that information, that a priori information about what kind of input data you'll have, and you know that most of your input is going to be small or almost sorted, then you can use insertion sort, because the average in that case is really what you care about. But when you have
Right.
no information at all like that, we worry about the worst case, right? Because anytime you are working with averages, average case analysis, you have to assume some prior input distribution. Only then can your average case analysis make sense. The other issue with average case analysis is that it's often mathematically very hard to do. So just to keep life simpler, we work with worst case, unless like the analysis is relatively simple. Like I had the analysis for Quicksort in the foundation video. So Quicksort and hash table operations, these are two exceptions where we actually worry about average case even in an interview, because for practical purposes, because these algorithms are randomized, they run very fast. So you can assume that they will reliably run fast even in an interview context. And so you can use their average case complexities as their practical running times. You shouldn't use the word worst case for those complexities, but you can say the complexity is going to be n log n on average. So I'll use Quicksort, something like that. That would work. But generally we worry about worst case. Ankita? Sorry, Karthik, I think you had raised your hand earlier. Karthik?
Yeah, so my question was in an interview when the first phase of the interview where the input set is small, would the interviewer expect us to use the insertion sort kind of an algorithm, which is, for best cases better? And then for bigger inputs, when the interviewer starts generalizing the inputs, would the interviewer expect us to use probably, merge or quick or something else?
No, so you should assume by default, for any algorithms problem, you should assume that the input can theoretically be quite large. By assuming that the input is small, you're assuming a best case scenario. You're assuming a friendly input. You have to imagine the interviewer as an adversary who will try to break your code or your algorithm by providing you an input that is as unfriendly as possible, which will make your algorithm run as long, take as long a time to run as possible. So that's why that's the worst case mentality, right? When we think about the worst case complexity, we have to imagine an adversary who's going to give us a really unfriendly input to try to make our algorithm run really long. So we want to optimize for that rather than optimize for. So the examples here that you see on in this lead code problem, these are just toy examples meant to clarify the problem. They are not saying that the typical input will be as small as this. They're just showing some simple examples, the kind of examples that you might draw on the whiteboard in an interview, just to make sure that you've understood the question, the semantics of the question. Okay, Ankita?
I had a question regarding the complexities. So if it's an on-site interview, in that case, you can go into detail at how you derive the particular complexity for a given solution.
Mm-hmm.
However, in case of online assessments, where you're supposed to, at times answer that, like come up with a solution and let us know what is the complexity.
Yeah.
So what's the right way to go about it? Is it just enough to just write it's n log n, or do we need to derive that as well?
So if you're talking with the interviewer, then yeah, you can talk about the complexity being n log n or n square. But if it's like a purely impersonal, coder pad kind of environment where your test cases need to pass, then if you code up selection sort or bubble sort, you're going to get a time limit exceeded error. So that's the way they evaluate you on, if they don't want a quadratic time, they want something significantly better than quadratic time, then your solution will time out. So, but if you have an interview in front of you, you can, I mean, you need to agree on what the final algorithm is before even trying to code it up. So you should have that discussion before you start to code. Otherwise, you might be wasting your time, since the optimum algorithm might be something different. Dinesh? So Dinesh, I think you're muted. I don't know if you're speaking.
Oh, sorry. Can you hear me now?
Yeah, I can hear you now.
Yeah, no, it just not that important question, but the thing is that since we consider heap sort for sorting, why don't we consider binary search tree for sorting?
We can. So that's called tree sort.
Yeah.
I don't talk about it because I'm not sure that people, trees is something we do in week 3.
Okay.
So understanding how tree sort works would require you to understand, how binary search trees are built in a way that they are balanced. So
okay.
That's something you'll learn in week 3. Yeah, but these, by all means, these 8 sorting algorithms are not the whole set. There are like hundreds of sorting algorithms people have invented.
Yeah.
Also, tree sort is harder to implement in an interview, so you wouldn't really, it would be you would be wasting your time trying to write all that code to insert and.
Yeah, but that's the confusion I have. Like in interview, do they expect to write a sort code? I think we discussed that on Discord, I think.
Yeah, they wouldn't normally expect you to write. So the problem that you're going to get in an interview most likely is going to be a problem, right? That means they already know that standard algorithms, standard sorting algorithms is something that is just a given. So they want you to apply those algorithms or take building blocks of those algorithms and apply them to new questions. Which is why it's unlikely that they will directly ask you to implement Heapsort, because there's no mystery then. If either you know it or you don't, right? And of course, the assumption is that you already know, so that wouldn't really test your problem solving if they just ask you to implement Heapsort. So okay, Lalitya, I don't know if I'm pronouncing it correctly.
So when we are talking about solving a problem, so when we are writing an algorithm for it, we select one of the algorithm out of it, and we do it. After the code has been completely written, we have to give the time complexity of it. We have to explain the time complexity. So do the interviewers also expect it to be proved as you have shown us in the pre-class videos using the mathematical derivation?
No, generally no. So you should approach time complexity and space complexity analysis in a top-down way, which means just mentally calculate what it would be and state what it is. Maybe give a few lines of explanation. That's all. And if they ask you for more details, then only you go and start doing all that full-blown analysis. So I go bottom up in the foundation videos, but in an interview, you should go top down since time is limited, and then wherever they ask for details, since you would have learned things bottom up, you can dig into those details, come down to whatever level of detail they want you to.
Sure, thank you.
Also, folks, once you have answered your questions, please lower your hands so that I know that I don't have anything unanswered. Dinesh, you had something more to ask, because I still see your hand up.
No, the thing is that I'm trying to remove that hand and I'm not able to.
Okay, I can lower it for you for now, but there is a button right there. Kalpana? I think Kalpana, you're still muted.
Yeah, can you hear me now?
Yeah, I can hear you.
Yeah. So my question is, you mentioned that nobody would ask any sorting algorithm kind of thing, right? So probably this lead code question is not valid then.
Well, that's what we'll come to now, because they have it as a medium problem. So why are they giving this? So we haven't yet completed this question. Yeah.
Okay.
So we've done those 3 inefficient algorithms, and then what are the efficient ones? We had merge sort, as someone mentioned, and quicksort, which is also a divide and conquer algorithm. Both of these are divide and conquer. What's the time complexity?
N log
N log n, worst case for merge sort, and n log n average case for quicksort. But as I said, you can assume the average case as the actual running time in an interview. If this was a university course, you would not be allowed to do that. But in an interview, you can assume quicksort will run in n log n time, because the probability of encountering the worst case is really small if your algorithm is randomized. So you have to ensure that you're picking the pivot randomly. Otherwise, some adversary could break your algorithm by giving you an unfriendly input that will make your algorithm run in quadratic worst case time, since he or she could see that you're picking the pivot in a deterministic way, and they could hack your algorithm so that on the particular array that they design, your code will pick the worst case pivot each time and thereby run into quadratic worst case time. Heapsort is the other one, which also runs in n log n time. Between merge sort, quicksort, and heapsort, what are the trade-offs?
Stability for merge sort.
Yeah, stability for merge sort. So merge sort is stable. Now, this doesn't mean it's stable by default. Obviously, you have to be careful when writing your code that you write it in a way that it's stable. But it's easy to make merge sort stable.
And merge sort needs extra space.
Yeah, stable but needs auxiliary space.
Quicksort in place.
Yeah, quicksort and heapsort can both be done in place. And it's possible to write code so that they both can be done in place. It's also possible to write code that makes any sorting algorithm stable, right? But it would require you to add auxiliary space. Like one simple way in which you could make any sorting algorithm stable is, instead of, take the input array that you are given and take the value of the number in that input array and the index of that number in the array as a pair, right? So if there are 2 copies of the same number in the input array, the indices at which they are found will still be different. So the copy at the lower index will be treated as being smaller than the copy at the higher index if you're comparing those pairs, right? The value comma the index. But when you do that, you're adding more space over and beyond the input, right? Because you have to store the indexes also now as your sorting algorithm is running. But that's just a general thing, you don't worry about it. But it's possible to make any sorting algorithm stable. But when we talk about stability, we are really talking about natural stability, right? Merge sort and insertion sort can be naturally made stable without adding any extra space beyond what the algorithm itself needs. Empirically, as I said, quicksort runs quite fast on typical inputs. Again, it depends on the input distribution, but for many use cases or most use cases in the real world, quicksort is good enough. So it's heavily used in libraries. Merge sort also is used in the form of dim sort, since your application might need stability. So wherever stability is needed, the underlying implementation is going to be some form of merge sort. And where stability is not important and you want your algorithm to run as fast as possible on a general input, the underlying implementation would, typically be quicksort, sometimes heapsort, but typically quicksort, because empirically it runs quite fast. Kalpana, you had another question? Basavaraja? Sorry,
yeah.
Kalpana, you had a question or you just forgot to go
No,
ahead?
I forgot. Sorry.
Okay,
Yeah.
sure. Basavaraja?
Yes, I have a question. Yeah, during interview, is it a good practice to tell the time complexity while explaining the logic of the problem?
Yeah, because how do you know it's the most efficient?
Yeah.
Right. So, I mean, you explain the logic, and then you derive the complexity, and then if it's not good enough, the interviewer will ask, can you do better?
Oh, do you need to derive the complexity, or can we directly say, okay, this is how this is the complexity of this algorithm?
Yeah, you should go top down. So you should be able to do it quickly mentally, and then just use 1 or 2 lines of explanation.
Okay.
To explain why you think it's order n square. And if the interviewer says, can you do better? That means you have to think of a better algorithm.
Okay. Yeah. Thank you.
Sudhir?
Hey, Omkar.
Yeah.
So you mentioned that stability in this particular example does not matter because it is a primitive, right?
Yeah.
And stability matters only in case of objects. So a general question for me is, it matters because of object equality, or is it like, say if the objects are immutable, then stability really doesn't matter, right?
Well, it depends on your application. I think I had like an example in the foundation videos, right, where you had like multiple fields in an object which you wanted to sort by. Now, it's not, when I said stability does not matter when we're talking about primitives, there is an exception though. If you remember Radix sort, you haven't come to yet, but Radix sort requires you to have stability in each pass, because without that your algorithm won't run correctly. So in general, yes, for primitives it doesn't matter, but if you are looking at the structure of those integers, or internal structure of that integer or string or whatever primitive data type it is, of course it can't be a float. So Radix sort applies only when your input is an integer or a string, you can say, but not for floating point numbers. So for those 2 types of inputs, stability could be important even though they might be primitives.
So if the field value of an object is not the same, then it's not a duplicate, right? So in the first place,
it's not. Yeah, if it's not the same, then it's not a duplicate. Yeah, but if it is the same, then it's a duplicate, right? So I think I had the example of log files in the foundation videos, which shows why you might want stability when there are multiple fields. So yeah.
Thank you so much.
So let's see, Vashisht.
Yeah, hi Omkar. So I usually see in these kind of sums they would mention like how much would the size of the input be, like 500K or something, and in the tutor, yeah, something like this. So in tutorial you mentioned like in general, like if the size crosses 1 million, then Quicksort would take the form of quadratic expression or something like that, right? So
No. Quicksort, randomized Quicksort will run fast even if the size is a million or more, as long as you are using a randomized version of Quicksort. So the complexity of Quicksort doesn't depend on the size of the input. It depends on whether your algorithm is randomized or not, the average case complexity. Also, it depends on the input, the distribution of the input, but I'll come to that later today.
Okay, sure.
Yeah.
Thank you.
Sujit?
Yeah, so my question is, what is the trade-off between the space complexity and the time complexity? So is there
it's not clear, right? Because here you're using more space in merge sort, but if stability is needed, then there's no option. And space-time trade-offs are actually, there's no universal answer for them, which is why questions which involve space-time trade-offs are good questions to ask in an interview, because they give you the opportunity to test the candidate to see if he or she can evaluate those trade-offs, right? And you'll see examples of that again today. Paul?
Yeah, I was just wondering, like, how do we kind of estimate how much space you're going to need for a merge sort?
Well, it's going to be order n. because the size of the auxiliary array into which you are merging the two subarrays in the worst case would be order n, right? The final merge that you do with the two subarrays
Okay, got it.
would need order n time. So order n, again, you have to think about the worst possible space complexity.
Okay.
So yeah.
Thank you.
Okay, folks. If you have any pressing questions, you can feel free to ask them right now. But otherwise, if you have questions specific to merge sort, quicksort, or Heapsort, let's take them later on. Okay, so please lower your hands if once, since I see 4 hands raised, I think I did answer all the questions. So there are 2 algorithms that still remain. One is counting sort and the other is, the other is Radix sort. So counting sort is useful when your input has a very narrow range of numbers. Another scenario in which it could be useful is when there are lots of duplicates. Okay, and I would say very, very few unique numbers. So if you have lots of duplicates, very few unique numbers, you might as well just figure out what that set of unique numbers is and with what frequency do they occur. Right, so that allows you to then directly do the counting and then create the final output based on them. If the inputs numbers are in a very narrow range, then also you can just count how many numbers of each value there are and then directly create the output from that, as I went through in the foundation video. So this is something that could be done in order n time if your range is narrow, right? That is, the range of numbers is a constant or the number of unique numbers in your input array is a constant, then you could do it in order n time. So if we used counting sort here for this problem, why? Well, first of all, is the range narrow? Well, we are talking about integers
50,000.
here, and the size of the input can be from 1 to 50,000. So if we just parameterize it as n, right, let's say size of the input is n, then the range of numbers in the input is really from minus n to plus n. Right, that's the range. So if I just counted how many numbers there are of each value from minus 50,000 to 50,000, or maybe I just track what the unique numbers are in that range. So I could do counting sort, and if you do that empirically, you will see that it does run faster than the other algorithms we have so far. It's not a very large range, but you might need to use some extra space to track those counts. The final algorithm that I did was Radix sort, which is basically an extension of counting sort in scenarios where the range is not so narrow. If the range is not narrow, you could look at, and if your input consists of integers, you could look at the values of the structure of those integers byte by byte or however many bits at a time you want, and then sort them in a right to left order, maintaining stability. And each time you sort a section of or all the numbers based on a section of those bits, you use counting sort. So Radix sort also, assuming that the number of passes is a constant, is going to be order n, right? 2 passes of counting sort, for example, would also take order n, right? So in this case, the values of the numbers are from minus 50,000 to 50,000. right? So how many bits, how many, even if integers have four bytes or 8 bytes or whatever your programming language has, how many bits are we really concerned about if the values of those integers are from minus 50,000 to 50,000?
32.
We don't need all 32 actually, because if you use 32 bits, you can actually go up to 4 billion, or maybe minus 2 billion to plus 2 billion, right? A range of 4 billion. That's why the number of IP version 4 addresses, for example, is 4 billion, because there are 32-bit addresses. So 2 to the power 32 is around 4 billion. How many bits do we need to look at to hit 50,000 or rather 100,000?
8-bit, I think 8-bit.
8-bit would get you to 256 again.
256, yeah. So
Please
something around 18 or something?
Yes,
16
16 would lead up to around 65,000. You know, the number of port numbers you have. If you're from a networking background, you know it's around 65,536, something like that. So 16 bits go up to 65,000, but here our range is from minus 50,000 to plus 50,000. That means 100,000, right? So need to probably go one more bit higher than 16. So maybe 17 bits or so 17 bits are what you look at, but I don't want to get into bitwise operations here, but negative numbers on, when you look at how negative numbers are represented in 2's complement, the first bit, the most significant bit is usually a 1. So 16 bits for the magnitude and the most significant bit for the sign. That's what you would look at. And 16 is convenient because you can do 2 passes of Radix sort looking at the least significant byte and then the second least significant byte. So looking at bytes at a time is also convenient from a hardware perspective. So I don't want to go into the details of Radix sort here because it used to be asked earlier, but it's not a common question nowadays. It's just something you need to know if you want to prepare for the worst case. So for your reference, I have all the sorting algorithms. I did post them yesterday on the Discord channel, but all the algorithms for this problem, I have the code for them, including counting sort and Radix sort. Okay, so this is one version of counting sort. There are a couple of ways of doing counting sort. So just look at this sample code later on if you are not able to implement these algorithms on your own. But if you feel uncomfortable with this code for Radix sort, just drop it, right? Because it's not common to be asked to code Radix sort. But Radix sort also runs quite fast on this problem, right? So counting sort and Radix sort both run the fastest. And that's why it's a medium problem, because you could use merge sort and Quicksort, but to really optimize it, you would need to go for counting sort or Radix sort.